Thank you for the invitation. It's a great honor to speak in your international PDE seminar. My apologies to those who've heard a similar talk of mine before. I hope it will not be too boring. The talk is divided into three sections. The first one is a revision, really, or just a recollection of some very classical spectral theory that much of it, but not all of it, you will find in Reed and Simon. But many PDE people, many in the PDE community have either, never paid attention, either forgotten it, and it is somewhat soft, but very useful. It's not to be underestimated at all. It's very nice. And in particular, the emphasis will be on the distorted Fourier transform, which actually is a very simple consequence of the Stone formula and the spectral apparatus, which is also quite elementary, which we'll now develop. So let me get started. So consider a Schrödinger operator on the half line. It's written as H. V is locally bounded. For convenience, you can relax this assumption. It is real valued. We pick as a domain the C2 functions of compact support, not form domain, but true domain. And we are interested in the resolvent of this. But it's important to realize you cannot talk about the resolvent without the notion of self-adjointness. To some extent, these two are equivalent. The resolvent in the upper and lower half plane. For every z that is not on the real axis, we want to be able to make sense of this resolvent, which of course is h minus z inverse. All right, how do we do that? Well, the beauty of the line is one dimension that you can actually give an explicit formula for this resolvent kernel in terms of special solutions, one of which is the Weil solution at x equals plus infinity. If you're on the whole line, you will have two of them. You will have one at plus infinity, one at minus infinity, which is the reason why the spectral measure for the whole line Schrödinger operator is actually a 2 by 2 matrix, a positive definite matrix, or at least semi-definite matrix. On the half line, it's a scalar valued object, which is why I am on the half line. So when V is 0, which essentially is the most trivial case, if the imaginary part of Z is positive, you have these explicit solutions here. They are exponentially decaying when x goes to plus infinity. So they're L2 at plus infinity, and they're generalized eigenfunctions. I don't want to call them true eigenfunctions because we are not imposing a boundary condition at 0. Okay, that's precisely what we're not yet doing. And the geometry of this map Z goes to I root Z is as shown. And this so-called Weil solution is unique up to a normalization. You can multiply it by any non-zero number. Now there is this classical notion going back to Weil, limit point cases at infinity. We want H to have a unique Weil solution, of course, up to this normalization. In other words, we do not want a full fundamental system to lie in L2, which then implies that every solution would have to be L2 at plus infinity, of course, only off the real axis. So imaginary part Z is not 0. This is the case, for example, if V is bounded at infinity, that's what this means, L infinity near infinity, but in fact, you need much, much less. So let's take a closer look at this. All you need is the Wronskian, okay? So suppose you have two solutions of this, call it eigenvalue equation, it's a bit of a misnomer, and they're both L2 at infinity. If the derivatives are also at L2 in L2, then you get a contradiction because then the Wronskian, which is a constant, will have to go to 0 along a subsequence, and that's impossible because this Wronskian has to be non-zero if they're linearly independent. Now, how do we justify this crucial assumption? So as a reminder, the Wronskian is, of course, psi prime phi minus psi phi prime, up to a sign. Some people change that, and this doesn't depend on where you evaluate them. The reason for this is that you have the same Z in for both of them. For example, if V is bounded at infinity, then you just write down the ODE, psi double prime is V minus C psi. Because we assumed V is bounded, the second derivative is in L2 at infinity. So by interpolation, the first one is also L2, and there you have it. Henceforth, we will always make this assumption, which people consider a mild assumption. Basically, any sensible operator is limit point at infinity. Now, in physics, you come up with sometimes these exotic creatures which are not limit point at infinity. We can ignore those altogether. That would mean if you are limit circle at infinity, which is the opposite, then you would need a boundary condition at infinity. So I think it's safe to say that nobody ever of us ever uses a boundary condition at infinity. Maybe I have to bite my tongue and somebody can contradict me on that. Is there a chat? Okay, not to worry about. If there are any questions, please interrupt me immediately. I have my volume on, so I will hear. So now we can just, up to normalization, assume that there is a unique solution, which is L2 at infinity for Z, for energies, if you want to call it that, of the real axis. Now, how do we justify the existence? How do we get the existence? Now I will use a self-adjoint extension of H. Remember, H was defined on a domain which are C2 functions of compact support in the open half-line. If you take any self-adjoint extension, for example, a Friedrichs extension, which only requires that the operator is bounded from below, then we have a resolvent because H is self-adjoint. So you can take any Z of the real axis, and then this is an L2 bounded operator. So therefore, this whole expression is L2. Notice how we applied the resolvent to the indicator function of 0, 1. In fact, you have a lot of freedom here. You can take anything compactly supported. But then, by construction, if you apply H minus Z to this psi, then that will vanish if X exceeds 1. And that's the luxury here of one dimension, because now you can just solve backwards by existence uniqueness, and you will have backwards meaning to 0. And you will have a solution globally on the half line of H minus E psi is 0. So you have to modify psi on the interval 0, 1, of course, from what it was defined here. Okay, but that's fine. So this you have to then modify. All right. So that gives you the existence, and uniqueness is by stipulation, by assuming that your limit point at infinity. What's a Friedrichs extension? I shouldn't really spend too much time on that. It's incredibly commonplace. You look at the quadratic form and you integrate by parts, which we can do on our domain C2 compacts. And then you get this formula. So for example, in the free case, when V is 0, you immediately see that the closure, what is the Friedrichs extension? It is the closure of the operator under this norm, which for the free case is remarkably the Sobolev 1 norm with a Dirichlet condition at 0. So the Friedrichs extension automatically gives you the Dirichlet boundary condition at 0. Another case where you can apply this, very useful for what I will say later, is if H is a non-negative operator, in fact, admits a factorization into D star D. D is first order. If you do that, then you will get a different Sobolev type norm with one derivative, and it's this one here. Okay, you just integrate by parts. And then you cannot simply conclude that F needs to vanish at the origin. So a Dirichlet condition, it depends on the behavior of U at the origin, which might blow up. It's all fine. This formula here, this norm, this Sobolev H1 type norm, but relative to U, will dictate to you whatever the boundary condition is. Okay. Now, all of us have come across, I think, this dichotomy at 0, where you either limit point or limit circle at x equals 0. What does this mean? In a nutshell, it means you can be self-adjoint with or without a boundary condition at 0. This might be astonishing to hear if you haven't seen it before, that you may not need a boundary condition at x equals 0. How can this be? Well, look at something very commonplace, a Bessel operator here, h is minus Laplacian on the half line plus alpha squared minus a quarter of x squared. The reason I wrote the index of the Bessel function as alpha squared minus a quarter is because you then get Bessel alpha, you get J alpha or Y alpha, okay? So if you look at zero energy solutions of this Bessel equation, you will have two, a fundamental system, and the x to the 1/2 plus minus alpha. So you immediately see that if alpha is 1 or larger, then one of these will not be in L2 near 0. So at alpha equals 1, for example, you get x minus a half, you just logarithmically fail to be in L2. And so then you do not need a boundary condition at 0 because you have to throw out the solution which is not L2. So you eliminate one of them, the two singular one, whereas if alpha is less than 1, both of them are in L2, and then you cannot make sense of self-adjointness of this Bessel operator on the half-line without a boundary condition at 0. And for a z different from 0, the fundamental system is given by Bessel J alpha and Bessel Y alpha. Okay? Now, notice that these potentials here, they are so singular that they fail to be L1, in fact, by a lot, unless alpha is a half. So if V is much better behaved, which means it is L1 near 0, then automatically you have a fundamental system near 0, which is both of which are L2. Both functions in this fundamental system have to be L2, simply by Picard iteration. All you need for Picard iteration is that the potential is L1 near 0, and then you can solve as you are used to. This is Dirichlet, this is Neumann, okay? Function vanishes at 0, derivative is 1, it's Dirichlet. Function is 1 at 0, derivative vanishes, that is Neumann. And that gives you your fundamental system, which is why if you are not L2, the literature singles this case out, and it's called strongly singular, because then you precisely cannot play the usual games, Dirichlet, Neumann, or whatever angle you choose. Yeah? So suppose your limit point at the origin, meaning that your strongly singular have to be, and like a Bessel equation with alpha greater equal 1 as we had before. Then H is essentially self-adjoint, meaning if you pass to the closure over that domain, of course, remember, we're always assuming your limit point at infinity. So your limit point at both 0 and infinity, then all you have to do is you pass to the closure. And then that is self-adjoint, and this extension is unique. In particular, this has to be the Friedrichs extension. And if so, then you have this fundamental but completely simple and elementary formula for the resolvent. That's why these notions are so useful. You take the solution which is L2 near 0, you take the value solution which is L2 near infinity, of course, for imaginary part not 0, and you divide by the Wronskian. That is when the argument of phi is less than the argument of psi. And if you have the reverse behavior, then you just need to flip, okay? That's the symmetry of the Green's function. And so that does what you want. It solves, you can solve H minus Z phi equals F, or whatever you want to call this. H minus Z F tilde equals F. And so you have the resolvent, and the exact same procedure works if you are regular, if the potential is L1 near 0, and then you must impose a boundary condition as it's written here, and you will then be able to write down the exact same formula which then tells you basically that you're self-adjoint, because having a resolvent off of the real axis is the same as being self-adjoint. So what is the Weil M function? Such a fundamental object. For simplicity, assume that you're regular, so that you're L1 near the origin and locally bounded, and of course limit point at infinity. So then you know that you can speak of Dirichlet and Neumann near zero. This is what I have here in terms of phi. Phi and theta correspond to Dirichlet, that's that column, and Neumann is this column, okay? And then remember that off the real axis, those, I should remark, those phi and theta are actually entire functions in Z. Very unlike the Weil solution, which has a root in it, so it's completely different. It's not entire. But these functions, which for the free case, by the way, the phi would be sine root Z x over root Z, and cosine root Zx, that would be theta, and that's phi. At first sight, they might not look very entire, but think of the Taylor expansion, you'll see that everything works out perfectly. These Taylor expansions involve only integer powers of Z, and they converge everywhere. So phi and theta are entire. Now, off the real axis, you write psi as a linear combination of theta and phi. But notice, somehow by force, we put coefficient 1 in front of theta. We can, of course, always write psi as a linear combination, but why are we allowed to put this normalization there? Well, very simply because the only case when we could not do this is if this theta went there at all. In other words, if it came with a coefficient 0. But that would mean that the Weil solution is entirely given, is a linear multiple. It's just a scalar multiple of phi. Okay, but then phi vanishes at 0 because it has a Dirichlet condition, and it's L2 at infinity because it's the Weil solution. But that's impossible because then it would be an eigenfunction with non-real eigenvalue of a self-adjoint realization of H, which cannot be, because then Z would have to be on the real axis. So that's the reason why we're allowed to look at this linear combination. And this creature is absolutely fundamental, and I'll go very fast here to save time. This creature is, of course, the M function. You can play some Wronskian tricks. Everybody knows these tricks. When you compute the Wronskian of psi and psi bar, you recover this fundamental formula here in this box. I'll put another box around it, that the imaginary part of M equals the imaginary part of Z times the L2 norm of this Weil solution, which we normalized. How did we normalize it? By this. This amounts to a normalization, of course. This yellow box there is a normalization because theta is uniquely defined, phi is uniquely defined. We write it as that linear combination. We know that we must be allowed to do this. And then you have this fundamental relation, and that means in particular that M is a Herklotz function. You can check M is analytic in the upper half plane, and this says that if Z is in the upper half plane, then M takes values in the upper half plane, it's Herklotz. And this is more than a convenience or curiosity. Here is a Wronskian relation in green that gives you the M function. So we will see how fundamental this Herklotz property of M is, because then you have the representation of such a Herklotz function as a Cauchy transform of a positive measure up to a linear correction, okay, which allows for growth at infinity. But that measure is no accidental creature. How could it be? It's the spectral measure of H. Okay, so let's do this a little bit more slowly. How do you get the distorted Fourier transform? You start from the Stone formula. How am I doing on time? Okay, not great. You look at the Stone formula, which allows you to compute the spectral resolution in terms of the jump of the resolvent across the real axis. Okay? E is the spectral measure, which is a projection value measure on Borel sets. And now just push a and b to the n, so a to minus infinity, b to plus infinity. And then this whole left-hand side becomes the L2 norm. All of this, no, I shouldn't have done that. All of this becomes the L2 norm because these e's go to the identity, and then you have that. The beauty of this is that you simply can write this resolvent as we did before in terms of these fundamental systems. So you have phi, you have theta, and you have psi. If you do this, and you do these totally elementary calculations, let me not spend too much time on that. What you will see is that because phi and theta are real on the real axis, they don't jump across the real axis. All of these terms cancel, and you're simply left with this very nice expression in the green box, which is really, you get just in 2-3 lines from what we did before. And if you stare at it, we should interpret this as a Blancharel formula, of course. Here, well, we'll have to unravel that. That's the M function. But what else could this be but some kind of Fourier transform of f at lambda? Think of the free case when phi x lambda is sine of x root lambda over root lambda, so it's a sine transform. Well, that's the odd. If you do an odd extension of f, it's just a Fourier transform on the line. And so this we need to interpret or understand whether does this limit exist or not, but clearly this should be f hat. And sure enough, here is the Herklotz representation, this here, which is so important that you have positivity of the imaginary part. It's a Ries representation type result. And once you use that, this is what you can plug here. Okay, that limit exists in the almost everywhere sense. Well, you have to be a little bit careful because we're making no assumptions whatsoever on the spectral type of H. It might have eigenvalues, it might have absolutely continuous spectrum, singular continuous. It makes no difference. It's all captured by this rho. If you have eigenvalues, rho will have atoms. If it's purely absolutely continuous, rho has a density in L1. If it's singular continuous, rho is singular relative to Lebesgue. It's all automatic. It's very remarkable. And so then you have the true Blancharel formula in the red box. Now, this whole story, remember, we assumed, well, where regular V is L1 near the origin, you don't need that. And this is a fairly recent story. There is a nice paper, amongst others, I should say. There's a community, Sturm-Liouville community, that has, to this day, continues the exploration of the spectral properties of such operators. A paper that has been very influential for my collaborators and myself is Gestesi-Zinchenko from 2006, where they present this short derivation via the Stone formula, and they say in their paper they are not the first to do that. But most importantly, they show that the same procedure works when V is not L1 near the origin. And like in the Bessel case, so important, because in applications, this is what happens. Now, missing in this red box, Blancharel, is the inversion formula. How do I recover f from f hat? Very quickly, you get that by Fubini and Blancharel. Not so surprising, because you have the unitarity property, so you can compute the inverse. Just out of curiosity, here's how you do this. You polarize Blancharel, that's that, okay? Then you have, maybe that's called Parseval, or I got the nomenclature wrong, I don't know. Now you plug in the definition of G hat as an integral against phi, this Dirichlet fundamental system function, if you want to call it that. And you interchange integration, and then you immediately see that, well, that has to be f of x. So you have your inversion formula just by Blancharel and Fubini. And so that's it. And in Gestesi-Zinchenko, so here is the free case. As I said, phi is explicit sine, cosine. You can compute the spectral measure, it's this here, just by looking at the M function. This is the M function in the free case. It's I root Z for Z in the upper half plane. So you might have eigenvalues if you do nothing to be afraid of. That means that that Herglotz spectral measure rho has atoms, okay? And they then give you this red box here, where the atomic part is simply the projection onto the normalized eigenfunctions, and the rest, assuming that V is vanishing sufficiently at infinity, then you actually have a density, okay? Then you have eigenvalues in purely absolutely continuous spectrum for positive energies. And the inversion formula then takes this form, okay? You have to take the atoms into account, the eigenfunctions, you project on them as we all expect. The spectral measure, so very important actually in PDE applications is the question whether or not a zero energy resonance appears. This is a curious phenomenon when you have a solution of H, F equals 0 and F is not in L2, in particular it cannot be 0. In one dimension, if V decays nicely at infinity, then the only thing, so to be a little bit more precise than decaying nicely at infinity, what you need would be XV is in L1 globally, okay? If that happens, you can find this in many places, like the famous Steiff-Trubowitz paper on inverse scattering. If XV is in L1 globally, then the only non-L2 solution of HF equals 0 has to approach constants at infinity, okay? The free case V equals 0 has a resonance at 0 because the constant function equal 1 is a resonance solution, H1 equals 0. So the point of all these formulas here is to compute the M function for the Bessel case, and I just picked alpha equals 1. So, or here suddenly it's called gamma. So if I pick gamma equals 1, then you get Bessel J1, Bessel Y1. What's remarkable, so from these explicit calculations, you find the M function is no longer a Herglotz function, and this should set off alarm bells in your head. Well, if we lose the Herglotz property, we lose everything. We lose the ability to make sense of the limit of the M function as you approach the real axis. This is not a technical issue. This kind of the key engine here breaks down. Well, what Gistesi-Zinchenko observed is that you can replace the Herglotz property of M function by a more fundamental Herglotz property, namely that of the resolvent itself. Okay, if you look at H minus Z inverse FF, then that function has a non-negative imaginary part, a positive imaginary part, if F is not 0, if the imaginary part of Z is positive. And so this holds irrespective of regular singular V irrelevant. It's just a much more fundamental Herglotz property. And then they replaced the missing M function, Herglotz, feature by that, and showed how you can still carry through this whole theory. So now let me show you one instance, which hopefully you will find natural, for linear PDEs, where this distorted Fourier transform and this spectral theory appears naturally, in particular for Bessel type. They're not exactly Bessel, they're perturbations of Bessel. And a new feature appears here, as you will see in a moment, that we haven't touched upon at all, and that is the semi-classical character. There was no H bar in what we've done so far. Of course, you can artificially put it in. The question is always what happens kind of for either in the limit of as H bar tends to 0, or rather for all uniformly for all small H bar all the way down to 0. Then it becomes more delicate. All right, so now here is the model. Consider surface of revolution. You can think of this truly as a two-dimensional object, or you take a compact embedded Riemannian manifold of dimension D, and you put it in D plus 1 dimension, and you rotate. Okay, so you let group S1 act. Okay, and the metric on this manifold is what's written here. This is the metric, and note Note that at the ends, I made a particular assumption. I made the assumption of conic ends. What that means is that this R of x should truly behave like a one-sheeted hyperboloid. That's what this is. If R of x is root 1 plus x squared, and think of 1 plus 1 dimension, so two-dimensional surface, well, that's exactly the one-sheeted hyperboloid. For example, well, if omega is the circle, remember omega was this compact embedded Riemannian manifold. If it's just the circle, then you get a classical surface of revolution. And now what we're asking is, how do the wave and Schrödinger evolutions behave in long time on such surfaces? In other words, do they satisfy either L1, L infinity estimates, as in the Euclidean case, Strich's estimates? And most importantly, how does the local geometry affect these long time evolutions, the behavior, the long time behavior of these solutions, the dispersive nature of these Schrödinger and wave evolutions? And so this story started kind of for me in 2005. I was at the University of Chicago at the time, and there was this excitement about developments, Bürg-Gerard Cvetkov and Nonin Machatsursky, etc., when the semi-classical microlocal community started investigating very actively what the effect of a trapped geodesic, a periodic geodesic, on the evolution might be. When the classical flow is trapped, that's the opposite of dispersion. Well, then if you quantize that, what is the behavior of the quantized flow? And notice that the one-sheeted hyperboloid has a unique periodic geodesic, which is unstable. So the geodesic flow is hyperbolic near that. Whereas if you glue in here smoothly a sphere, piece of a sphere, it has many stable geodesics, periodic. How do you see the distinction between these radically different geometries in the evolution? That turned out not to be such a simple question. And so let me try and give you the answers very rapidly give you the answers. So there are a number of papers. This is the culmination of, well, let me see. So this theorem 1, what you do is you separate variables. Very simple-minded, but kind of, as we shall see, unavoidable. And the y-ends are, if you have a sphere, the spherical harmonics. For the circle, they're of course just e to the I n theta, theta being the angular variable. And so we decompose into fixed angular momentum via the spherical harmonics y and the eigenfunctions of the Laplacian on the compact Riemannian manifold omega. And f is only allowed to depend on arc length along a generator, no angular behavior. And then you see that for such data, these evolutions have the Euclidean long time decay in the uniform sense in L infinity. So if you recall, the Schrödinger evolution on a d+1 dimensional Euclidean space has this, I'm accidentally erasing, has this, no, wrong color, long time decay. By this, I mean, I'm trying to emphasize that. And here, that's nice, you have the exact same norm as in the Euclidean case, albeit, of course, L1 has to be expressed relative to the Riemannian content on the manifold, Riemann volume, Riemannian volume. And the wave evolution ditto. You need a derivative as always. Now, what happened to this question about local geometry? Hyperboloid on the one hand, is gluing a sphere there in the waist on the other hand. Well, all of this is now hidden here. So the conclusion of that theorem with regard to that question is that the long-term behavior is independent of the angular momentum. N doesn't appear here. The dimension appears here. but the angular momentum sits in the constant. And then the big question that took actually a lot of effort to resolve is, how does this constant depend on n? How does it grow in n? And I can tell you immediately what the answer is. And the slides below will exhibit some estimates to this effect. Here, this constant grows at most polynomially in n, so n to some power p, whereas here it grows like super exponentially, n squared log n cubed something. I haven't worked out the precise growth because it's not useful for me. And there is a manifest difference between these. In the polynomial, if you have polynomial growth, you can sum up, after doing separation of variables, you can brutally sum them all up. And the price you pay for this polynomial growth is only a finite number of derivatives in the angle. Whereas exponential is absolutely impossible. If it were purely exponential, you could do analytic data. If it's super exponential, forget it, okay? So you cannot sum any of this up. And that fits perfectly with the known instability quasi-modes with Ralston constructed on such surfaces. Okay, it's just impossible if you have a lot of stable geodesics. Your dispersive decay has uncontrollable growth in the angular momentum. So that's in this local geometry, does not affect the rate of decay, meaning the power law. And then on the one-sheeted hyperboloid, you have this PB. I suppose that means power behavior, growing like a polynomial or polynomial behavior, polynomial bound. And if the local geometry is bad, meaning you have positive curvature, a lot of stable geodesics, you have the super exponential growth. All right. Now, okay, a remarkable feature here is some non-Euclidean behavior that's kind of nice, and I would like to show. You can beat the Euclidean growth for fixed angular momentum. That is this strange minus sigma here. So you might say, how on earth can you beat the Euclidean power law? Well, the answer is only by putting in these weights here. So both your data have to be localized, and you as an observer have to be near the origin if you want. You cannot move with the crest of the wave. If you do that, you cannot beat the Euclidean decay law. But if you stay put as an observer, you will see more rapidly decaying tails. And the reason for this is that, heuristically speaking, that you have these geodesics, if you perturb them slightly, because of our assumption of conic ends, they will unravel and get sucked into the conic ends. And precisely as an observer, after a long time, which means this constant, that the larger this constant is, the longer you have to wait before you see any of this. As an observer, you will then eventually see how all of the flow just evacuates into the conic ends. And that sigma cannot be taken arbitrarily large. For zero angular momentum, this effect is absent. It truly only happens if you wrap around, so to speak. Right? So now, let me not go into the proof method. So to the organizers, I have 10 minutes. Is that allowed?
Yes.
10 minutes, okay. Proof method, well, you separate variables. The spectral theory I spoke about before, perhaps at too great of a length, comes in because you end up with Schrödinger operators on the line of this form. Well, you compute fundamental systems. The whole issue then becomes computing very precisely the behavior of the spectral measure at near zero energies. Of course, zero energy are the most important energy. They dictate the time infinity behavior of the dispersive evolution. Why? Well, because the Schrödinger flow or the wave flow are in some sense Fourier transforms of the spectral measure. And we all know that decay is dictated by singularities of that spectral measure, which really only can occur at the origin. And the smoother the spectral measure is at the origin, the faster you can make this decay. All right, I will not go into this to save time. Let me talk about, as you see, there is a lot going on here. I'm happy to share these slides in case anyone wants to see them. I will send them to the organizers. Now let's look at nonlinear PDE applications of such stories. First, let me mention a little bit the literature. So Gongchen and Pusateri in late 2019 studied small data global asymptotic behavior of one-dimensional cubic NLS with a potential. And they used the distorted Fourier transform as we constructed above to derive the correct behavior for both V having a zero energy resonance or not, and Pierre Germain and Fabio Pusateri, who are involved in a kind of a hot topic these days, Klein-Gordon kink, the behavior of kinks for nonlinear Klein-Gordon. There's also a very long paper by Delors and Masmoudi on that. So what I would like to talk about is some work that Joachim Krieger and Xiang Miao and myself posted not long ago on the archive. It's a little bit of a long story, and this is the rigidity of equivariant blow-up solutions for critical wave maps. So a critical wave map is just a wave map in general. It's a wave equation, a solution to a wave equation taking values in a manifold. This may sound bizarre, but you can perfectly make sense of that if you look at the Lagrangian formulation, you look at critical points, which give you the wave dynamics. And then this formula pops out. In fact, the important thing to note is that box U is perpendicular to the tangent space. This is for the sphere. You can take any target manifold you want. And then you have to be perpendicular to the tangent space at U of your target manifold M. This doesn't look like a PDE, but you can immediately transform it into one by means of the second fundamental form. And that is exactly this. What's staring at us here is some expression of the second fundamental form into which you stick the tangent vector fields dtu and dju, where j are the spatial coordinates. And then you have to contract that with the Lorentz tensor. That is why you get the Minkowski metric here. Okay, that is all unavoidable and dictated to you by the geometry. Because this is a wave equation that has a conserved energy, there is one family that stands out and has been studied for decades. These are equivariant wave maps. What do? They commute with the action of rotations. So in the domain, Lorentz space, you can write as R cross, in this case, R2. I will comment on the role of R2 in a moment. It's no accident. So R cross R2, you let rotations act on R2. If that action commutes through the wave map, meaning the target gets rotated, then you call this one equivariant, provided a rotation transforms into the precise same rotation with the exact same orientation. If you do it twice, you have two equivariant. You can do minus two equivariant, doesn't make a difference. Yeah? Only the absolute value, the orientation doesn't make any difference. Why are we looking at 2 dimensions? Because you can always rescale a wave map. You can take your wave map, U, Tx, and rescale it in this fashion, lambda t, lambda x. Especially in this formulation, which is equivalent, actually, somewhat surprisingly to that. You will immediately see you don't change that the image is perpendicular to the tangent space. By the way, this is the exact Lorentzian analog of harmonic map equation when you have the Laplacian perpendicular to the tangent space in the normal bundle. So it's the Lorentzian analog of harmonic maps. So under this scaling, your wave map remains a wave map. And then if you check exactly in dimension 2, the energy called this new wave map u lambda, the energy of u lambda will be the energy of u. So the energy is scaling invariant under this natural rescaling precisely in dimension 2. And this has fundamental consequences. It means in particular that singularity formation is not penalized by the energy, only in dimension 1, so 1 plus 1 dimensional wave maps. There you have global regularity. Now, it turns out, and this is some observation that Krieger, actually it's a construction and a fairly lengthy one that Krieger, Totaro, and myself made a while back. And we relied on this paper by Gestesi Zinchenko because we have to construct, we have to use the distorted Fourier transform and Blancharel very heavily. And so we constructed for the critical case blow-up solutions which are rescaling of the harmonic map of degree 1. So there exists this harmonic map only in degree 1 for equivariance. For every equivariance class, you can find a harmonic map which goes from the North Pole to the South Pole, and it will have growing degree depending on this rotation, okay? The polar rotation. But let's just look at one equivariant wave map. It has a totally explicit formula. The azimuth angle on the sphere is twice arctan r. As r tends to plus infinity, you get twice pi over 2. And somewhat strangely, the rescaling of that harmonic map was prescribed a priori. And this is small in some sense, but you cannot contract. You cannot set up a contraction mapping by naively plugging this into the wave map equation and hoping that you can use bounded contraction to eliminate that. Of course, in suitably chosen topologies does not work. So that epsilon has two pieces. One that is something like an elliptic profile modifier of the Q, and then a truly small piece that you can contract for, okay? And nevertheless, this epsilon is truly small in the sense that if you look at blow-up time here is blow-up time location is t equals r equals 0. And the energy computed in such slices will evacuate to nothing. So whatever excess energy you have on top of the energy of the ground state harmonic map has to be radiated outside of the light cone along characteristics, of course. Okay, so like that, all this excess energy will vanish. Let me go, because I'm really doing badly on time. Let me go to the theorem. I look at all this. This is a long story. Theorem. So this is the paper that proves that theorem, unfortunately a little bit long. What we posted on arXiv has 300, almost 350 pages. Welcome to this field. If you take a perturbation, so I should say that I have to explain how we even perturb non-equivariantly these equivariant blow-up solutions. The way we do this is to use an ansatz that was already introduced in a very nice paper on harmonic map heat flow by Davila, Del Pino, and Vey, where you look at the tangent space at phi, and then you use a particularly chosen orthonormal frame, namely the one of spherical coordinates. So you have this and this. These are the spherical coordinate vector fields on the sphere. They are E1 and E2 normalized. And then these are the ones you solve for. And that's a quadratic correction. And you pick it so that it's actually parallel and small, parallel to the wave map vector. So the blow up, this phi itself. And here is the explanation of that frame. And then what we say is that if initially phi 1, phi 2 are small, but they have to be chosen, we take s equals 100, by the way. If they're chosen small and supported away from the light cone initially, then you can give a full description of the blow-up solution. And it turns out that if you blew up, as we do, at space, time, location 0 initially, after this non-equivariant perturbation, you will still blow up at space-time location 0. And the reason for this is that the blow-up itself is generated by a shock along the light cone, and your perturbation is much smoother than that shock. The Q, the blow-up solution, is not smooth as you cross the light cone. It is, of course, in the well-posedness space, which is energy space. It is better than that, more regular, but it is not C infinity. And you choose your perturbations regular enough so that that irregularity has to be preserved. And then you find this expression where these R's and L's and this is a dilation symmetry. So you have 6 symmetries acting, physical symmetries. You have the Euler angles on S2, those are the R's. That here is a rotation in S2 on the sphere. That are Lorentz transforms. So that's 3 parameters, that's 2 parameters, and that's 1. And if you check it, you will see that the linearized operators, of which there are actually infinitely many, have a 6-dimensional family of 0 energy solutions coming from the symmetries. And these you control, okay? You need to control those. And a few years ago, not many, like 3 years ago, there is a deep work by Deukert's Giacchinic Mel, which classify non-equivariantly what kind of behavior you can have at most for non-equivariant blow-up for such critical wave maps. And they find precisely, they classify it by such a formula without, however, being able to say anything about the asymptotic behavior of the symmetry parameters. So our construction fits into that classification of Deukert's Giacchinic Mel and also provides convergence of these symmetry parameters. Thank you very much.